Recording in progress. Let's share the whole damn screen. Let's move this over here. Let's turn that on. Cool beans. Stop doing that. Go away. There we go. Let's do that. Let's make sure we're on. Here. Why aren't you on? Select. Why aren't you on? Problematic. Oh, because you have problems, that's why. Okay, there we go. Like the mittens, they're really adorable. For that. December 5th. Anyone know what's special about today in American history? It is the day they repealed prohibition. It's kind of a big deal. Called Prohibition Day. I think if they call it Anti-Prohibition Day. All right, so let's see here. It's 10:30. We should get going. A few things. So just so you all can see on our Canvas page, if you scroll down a bit, there's the survey, which I would please ask that you all take at some point before the end of finals. It probably takes like 5 or 10 minutes. Again, I'll remind you, it is anonymous, so I won't know who has written what. Hopefully you have good things to say, but if you have criticisms or critiques, those are also very welcome. Please just be honest and answer truthfully. My boss will compile the results and then send them to me, but I won't know who has written what unless you identify yourself. And then what I really wanted to get to was just final exam materials here. We have so this handout here is the first final review, and there's solutions there. And then there's also this other handout, which is the one that says final review Challenor. And yeah, my intention is hopefully tomorrow to record a video writing the solutions to that. So I'll both post a video for that and also post solutions to it. I might not get it done tomorrow, but certainly I need to get it done tomorrow if I'm going to do it. So I'll try to get it done tomorrow. If not tomorrow, Saturday morning, probably at the latest. Yeah. Okay. And then below that, we have a couple other things I thought were worthwhile. We have this list of final topics from Lewis's class, which I think is which I think we're going to talk about for a minute here. Which take your time. We'll just click on that instead. Yeah, let's do that. So it's kind of got by chapter the things he expects you to know if you're now I know your teacher isn't Lewis, but it's a pretty general list, right? Like it's very applicable. Dell's list would probably be more lengthy or in-depth or specific, but same idea. And then lastly, there is a practice exam from Alvarado's class. So lots of practice materials. If I see solutions for his practice final posted, I will post them. If I don't see them by, when's your guys' final? Oh, you got plenty of time. So hopefully he'll post them before your final, but if he doesn't, I will write some up. But he usually posts his practice final solutions pretty quickly. Questions about any of this before we get going today? Yeah. Monotonicity, that just means increasing, decreasing. So a function is monotonic if it is increasing always or decreasing always. But basically, when you look for intervals of monotonicity, you're looking for where it's either increasing or decreasing. It's kind of like how we use the word extrema to account for both maxima and minima. It's really just like laziness, to be honest. Like I'd rather not write two words. I don't want to write increasing and decreasing. I'm just going to write monotonic instead. Yeah. Okay. Let's see. I feel like there was something else I wanted to mention here, but not finding it in my brain. So, all right. If I find other useful things to post on Canvas, I will post them in this final exam prep area. Do you guys get notified when I post stuff? No? Like in the modules? Okay. So if I post something new, I'll post an announcement as well so that you will be aware that there was something new there. So for question one, I believe I noticed in your class yesterday that Dr. Dedell started talking about some antiderivatives. Is that going to be on your final? So I'm seeing some yeses and some nos. All right, then. So here's what I propose we do. We'll spend maybe 10-ish minutes just kind of talking about the content of the final, kind of going through chapter by chapter and so really that's why I printed out a copy of the syllabus. I like having the syllabus on hand, so I can just kind of look through and be like, okay, like what do I need to know from this section? So I say we go through that briefly. We can kind of discuss what might occur on your final, and then we can spend a little bit of time talking about antiderivatives because it's going to be on your final. We should talk about it. And then also because it's definitely going to be something you're going to be doing next quarter in 17B. So it's not just like a no purpose thing. Like sometimes at the end of the quarter, like at the end of 17C, you're going to learn some probability stuff. You'll be like, why are we learning this? And like, good question. Because you're probably right. You don't need it for the next quarter, but that's not true here. Here, antiderivatives is definitely going to be what you start with in 17B. So it's worth spending some time on it, especially if going to occur next quarter and it's on your final. But let's go ahead and look at just kind of what's potentially going to be on our final. And I'm looking at both this here and as well as, yeah, that over there. So, chapter 1. Let's see, looking at the syllabus, we have preliminaries, elementary functions and graphing, one full lecture on transformations of functions, log transformations, log, semi-log plot. So what I'm seeing from chapter 1 really is the log, and semi-log stuff. As well as just recently, sequences. Right, that's section 1.6. The other stuff in chapter 1 is more just kind of a review of pre-calculus that they're kind of already expected to know. So those things certainly are built into other material you're going to be tested on. But as far as what feels like topics worth reviewing are those things. Specifically for log and semi-log, knowing what being linear on a semi-log means and what being linear on a log means. Right? One of those corresponds to your original relationship being exponential. The other corresponds to your original relationship being power function. Also, if you have questions along the way, please ask them. All right, to me, and so I'm also looking at Tim Lewis's handout here. Yeah, that seems like pretty much all he's saying there. Yeah, question. Discrete time models. So those are kind of like when we were actually, I think, gosh, I believe last class we were talking about the stability stuff and the the difference equations. Different. So like discrete time models are kind of like what we were talking about last class. Basically, functions where you're not just plugging in any value, but you're like letting the amount of time increase by 1 every time. So kind of like these recursive functions where you have, I think we used q, or like where n sub t plus 1 is equal to some function of n sub t. Like, I'm trying to find my examples from last time. Sorry, I've got lots of notes over here. What's that? Well, no, that's a different, not that that couldn't come up, but that's not quite exact. That's an exponential growth decay kind of model. This is more like something like last time where we were talking about how like the drug injection every 6 hours and how the amount of drug in the next injection was equal to 4 milligrams per milliliter plus a quarter of the amount of drug left over from the previous injection. This is what we mean by discrete time models, where every discrete, when you see the word discrete, that just means like kind of like the counting numbers. Like we're only letting time be nice numbers like 1, 2, 3, 4, 5, etc. Right? We're not saying like you could have like 37 seconds pass by. Right? Like it's very kind of nice numbers. That's what the discrete part means. So we're just saying, oh, at the next time interval, what's happening? At the next time interval, what's happening? So on and so on like that. All right. I will also point out on this list of things that from Tim Lewis from his class, he also then references some problems from each section you could work on as examples of things you might want to try. So I would encourage everyone to look at that handout posted on Canvas as well. Let's take a look at chapter 2. Where did my chapter 2? Chapter 2 is limits. All the limits. So while I feel like you won't really have a whole lot of tests on chapter 2 in kind of the original way, like you won't be asked to evaluate limits the way you were in midterm 1, you will have some limit questions on your exam, but they'll probably be more like L'Hopital's rules kinds of limits. So limits are going to come back, and that's kind of all the limits. So we have, right, the limits as x approaches some number or as x approaches infinity. And this is going to pull in L'Hopital's rule, even though I know that's a later section. Also, continuity. I could definitely see someone asking a question like, where is the following function continuous? For example, it's typically a piecewise function. Where is f of x equal to e to the x plus 1 when x is less than 0? Cosine of x plus 1 when x is between 0 and pi, and the square root of x plus 2 when x is bigger than pi. Where is this function continuous? So really what they're asking there is, where is it not continuous? And then the answer is everywhere except for where it isn't continuous. What else in chapter 2? I mean, I know limits is kind of a big topic here, right? Because there were a lot of things with limits, but I think I imagine the limit questions you will see will be mostly L'Hopital's rule type questions. Might not be entirely right. Again, I'm giving my best guess. right? No guarantees. All right. Limits and continuity. Chapter 3. Chapter 3 is all the derivative stuff. So first off, the limit definition of the derivative. So we need to know that the derivative is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. There are other ways of writing this, but this is the way most people teach it and write it. You may or may not be asked a question like this. Sometimes people say, well, we've already done it on the first midterm, so we don't really need to ask a question like this. Other people totally feel like we should ask a question like this in the final. So yeah, it's hard to know what your teacher might do, but definitely something you're expected to be aware of for sure. And then what else do we have here? Just looking at our list. So derivatives, differentiability, higher derivatives, power rule. Yeah. So differentiability, that's just a word for where is the function differentiable. So some examples of functions that aren't differentiable everywhere. Something like the absolute value of x is not differentiable at x equal to 0. My other favorite is f of x equal to x to the 2/3 is also not differentiable at x equal to 0. Those are functions that have either corners or cusps, or as I just call them generally, pointy points at 0, right? They would hurt if you got poked with the graph at that point. It's not smooth. And then we have all the derivative rules. So we have the power rule, the product rule, the quotient rule, the chain rule. And we also have the derivatives of all types of functions. So the functions we have to be able to take derivatives of are obviously powers. So like x to the n. What else? What other functions do we have to be able to differentiate? Broadly, like as categories. Say that one more time. E to the x, yep, definitely. Or even any base to the x. The difference there being that for b to the x, right, for e to the x, the derivative is e to the x. For b to the x, the derivative is b to the x times the natural log of your base. We also have natural log of x and as well log with a different base. The derivative of the natural log of x is 1 over x. The derivative of log base b of x is 1 over x times the natural log of b. What else is missing from my list? Trig functions. Yes, the trig functions. So all the trig, sine. I heard an alert of some sort. Oh, all right. What magnitude? We should totally take this opportunity to talk about how earthquakes are measured on the logarithmic scale. The trig, sine, cosine, tangent, cosecant, secant, cotangent. Cool. Am I missing anything? I think that's it, right? Those are kind of all the functions we're. Oh, wait, there's one other function that I can think of. It's kind of like a trig function. Arctangent. But I believe that's the entire list of things that you have to know how to take the derivative of, combined with the rules, the quotient, product, and chain rule. I think, right? There's nothing we're missing here. It feels pretty complete. I think so. All right. And then also in chapter 3, gosh, chapter 3 has like a lot of stuff in it. So after all that goodness, then you have implicit differentiation. And then finally, related rates. Not even finally. Geez, holy smokes. I'm trying to fit this all on one page. There's like 2 more topics here. Good God. Chapter 3, continuing on, implicit related rates. We also have linearization. Oh, sorry, I skipped something. Sorry. Exponential growth and decay. So that's your y equals c e to the kt situation. And then I'm going to skip the derivatives of the inverse and logarithmic functions because that's kind of something we've already talked about with our whole list of derivatives here. And then finally, in chapter 3, linear approximations, aka linearizations. So it would be wise for you to take some time to say, okay, like either make up an implicit differentiation problem or find one and do it. Related rates, exponential growth and decay, etc. And again, there's lots of problems on the handout, so there's definitely lots of opportunity to practice these things. All right, we're almost done with listing of the things. Chapter 4 is where I should probably look at this list over here. Sure. So chapter 4, maxima and minima, or more generally said, extrema. And we have 2 types, right? We have absolute extrema. Typically, although not always, on a closed interval is usually where we are asked to find them. And then we have relative extrema. Or if you prefer, right, absolute is also called global extrema. Relative is also called local extrema, right? Those are just as good words to use. What else do we have here? I mean, to me, all the stuff I'm about to say really just feels like it's in the guise of graphing, right? So relative extrema, maybe not so much global or absolute extrema, but relative extrema, and then you have all your increasing, decreasing, aka your monotonicity. The fancy word, yes. And then you have your concave up, concave down. But all of this is really just graphing. Not that you couldn't be asked about it without a graph, but usually if someone's asking you about where you have a max or min and where you have increasing, decreasing, concave up, concave down, inflection points, all that stuff usually leads up to then graphing the function that you're being asked about. I don't recall, so please remind me, Dr. Dell did talk about the mean value theorem, right? So that's also potentially on there. So mean value theorem, the short of it being that somewhere on your interval, there's a place where the derivative is equal to the slope of the line connecting your endpoints. There's more to it than just that, right? This is the very brief, right? I didn't write all the things about how like the function should be continuous on the interval and differentiable on the interval. But that's the gist, is that right there. All right, last couple things in chapter 4. We have L'Hopital's rule. We have optimization. And finally, we have the stability of fixed points in recursions. Interesting. It is interesting to me that the syllabus does not have antiderivatives on it. Yeah, I feel like it used to have antiderivatives on it. Maybe they got moved to somewhere else, like the next quarter. Well, yes. Oh, yeah. So I would, and I would definitely, I would go back and I would classify, so yes, and I would classify Newton's law of cooling under right here with the exponential growth indicator. So that also goes with this. But we can certainly talk about that a little bit more. So it's not a short list of things, right? It's kind of a lot. It's kind of and varied topics, right? So make a plan, right? You have to spend time studying. So, I mean, here's the real truth. You should do as many math problems as you can, right? The way you're going to learn the math is sitting down and doing math. Like that is, I mean, I don't know how other people learn math. Maybe some people do it differently than I do it, but the only way I ever learned math was like trying to do the problems. Be like, okay, I did that one wrong. Or like it made sense when I did it. Let me try another one until like it really kind of clicked. So for some people that takes more time than other people, right? Make sure you are using the time between now and what, next Thursday. And I know you have other finals, right? You can't spend all your time doing math. We wish we could, but I wish we could, but right, plan accordingly. All right. That said, let's talk. So we can't. Do you want to see like a Newton's law of cooling example? Sure. And then I do think we should get into antiderivatives a bit. So Newton's law of cooling. I think it's funny that it's called cooling because technically it's Newton's law of the temperature of your thing getting closer to the temperature of its surroundings, right? So it might be cooling, but it also might be warming. Um, so do I have an example ready to go here? Probably not. Sure, let's just make up some numbers. It'll probably be terrible. So I like to think of the example of trying to make your beverage colder. So we bought some, I don't know, some beer at the store. So at the store, they didn't put it in the fridge because they've got so much stock. The beverage was a very warm 70 degrees. Ugh, no one would want to drink that. 70 degrees Fahrenheit. Um, we take it home, put it in the freezer because that's the way to make it colder faster because you want the difference in temperature to be as much as possible. The freezer, which is at, I don't know, what's your freezer at? What's my freezer at? 32 degrees, I think. Maybe let's just say 30 degrees so the numbers are easy. That's probably too cold. You probably start like freezing things you shouldn't be freezing, but whatever. Sure. 20 minutes after doing this, the temperature of the beverage is 60 degrees. How long until it is 40 degrees? A reasonable temperature to drink it at. I don't know. Maybe that's probably too cold. Whatever. It's not the point. The point is the math. Okay, so when you see Newton's law of cooling question, I never remember the formula. Like it is not a formula that will ever stick in my brain because it just doesn't. What I do remember is the following: that the rate of change of the temperature. In fact, let's actually back up for a second. We should label a few things first. So let's say that the typical notation here is capital T of time is the temperature of your thing, of the beverage in this case. Beverage, I can't spell beverage. It's all right. At time T. And then T sub S is equal to the temperature of the surroundings, which is 30 degrees. Some people also like to note the initial temperature of your thing, but I feel like we know what that is, right? We know that T of 0 is 70 degrees. You can memorize the formula. I can't. So here's what I remember. The rate of change of the temperature should be proportional to the difference in your temperature and the surrounding temperature. And yes, in fact, I can even write the words down. So the rate of change of the temperature of your object is, that's what the equal sign gives us, right? The equal sign is the word is in English, is proportional to, that's what the K is giving us, the difference in the temperature of the object and the temperature of the surroundings, or of the environment. To me, my brain has to start here because that's just what that's the setup, right? The Newton's law of cooling says exactly this, that how fast the object cools is directly proportional to how big the difference between the temperatures is. So the greater the difference, the faster the rate of change. The smaller the difference, the slower the rate of change. And then this immediately leads us to the temperature of the object at time t is equal to, oh, nope. I always, not that, sorry, not quite, apologies. The difference in the temperatures. So the temperature minus the surrounding temperature is equal to CE to the KT. That's how I usually get there. So the temperature of our object, that's a T of little t, I know that looks terrible, minus the surrounding temperature is equal to CE to the KT, where we still have to figure out what C and K are. Now, there is a way to get there faster. Like you can memorize that C should be, I don't remember what it should be, honestly. We'll figure it out though. So then we're just going to start plugging in the information we have. So here's what we've got. We've got the temperature at time t minus the surrounding temperature is equal to CE to the KT. And here's what we know. We know that at time 0, the temperature was 70 degrees. And then we said 20 minutes later, the temperature of our beverage was 60 degrees. And also we know that the surrounding temperature is 40 degrees. 30 degrees, apologies, 30 degrees. My freezer is too cold. With all that, we should be able to find C and K. So I'm going to isolate this and say that the temperature at time t is equal to 30 plus CE to the KT. And then, like a typical exponential growth or decay problem, plug in my data points to find the constants C and K. So first I'm going to plug in the easier one, the 0 one. If I plug that in, I'm going to get, well, T of 0 is 70 equal to 30 plus CE to the K times 0. I probably did myself a disservice by adding 30 to the other side here, but oh well. I can subtract it back over and say, great, 40 is equal to C. Typically, this value here is always the difference between your surrounding temperature and your initial temperature, or your environmental temperature, the difference between your environmental temperature and the temperature of your object at time 0. But I don't think you should spend time or brain space memorizing that. So then we go back, we rewrite our model. Now our model is T of t equal to 30 plus 40 e to the KT. We can see, of course, that if you plugged in 0 for T, you would get 70 for the temperature. And then we're going to plug in this other data point. So the temperature should be 60. And the time should be 20 minutes. And then we'll solve for K. So subtract 30, divide by 40, equals e to the 20k. And then take the natural log of both sides. So the natural log of 3/4 equals 20k. So the natural log of 3/4 divided by 20 is equal to k. So if they had just asked us, what's the temperature at any time t, we could say, oh, well, that's just the model. And the temperature at any time t is going to be 30 plus 40 e to the k times t. And an easier question to answer next would have been, what's the temperature going to be after 60 minutes? But that's not what I asked. I asked, how long until the temperature gets down to a cool 40 degrees? So as is typical with these exponential growth and decay problems, whether they're regular ones like with bacteria or radioactive material, or the ones like this where it's Newton's law of cooling, it's always the same stuff, right? You're always either told plug in this time to find this value, or set the function equal to this value to find how long it took to get there. It's almost, I mean, okay, occasionally there's a slightly variation on that, but almost always it's one of those two types of questions. Here, they've told us we want to know how long it takes until the temperature gets to 40. So we're going to set the temperature equal to 40. And yeah, we can make this fit here. No, we shouldn't. We shouldn't make it fit. So write legibly and largely, not small and cramped. You can give me that feedback on my evaluation. Please write better. If you write that, I'll laugh, which is totally fine. So here's what we've got. 40 equal to 30 plus 40 e to the whatever. So subtract 30, 10 equals 40 e to the whatever. Divide by 40, so you get 1/4 equal to e to the natural log of 3/4 over 20 times t. By the way, if you don't like writing this terrible garbage for k every time, you could just write the letter k until you get to a place where you actually need to plug it in. Like you could be writing 40 equals 30 plus 40 e to the kt, and then subtract 30, and then divide by 40. Take the natural log of both sides. Natural log of 1/4 equals k times t. And then you can be like, oh yeah, k is the natural log of 3/4 over 20 times t. As long as you are very specific that you know what k is and you've written it somewhere like, oh yeah, k is this number over here. I think it's totally fine to do this so you don't have to write that garbage like in 5 steps or 3 steps or whatever. And then we can solve for t and get 20 times the natural log of 1/4 divided by the natural log of 3/4. Whatever that number is. All right. Questions about that? Sorry, I'm looking for my other notes that I was looking for. Where'd you go? Gosh, too many papers. Anyway. What do you mean? Like, sure. Oh, so you have to like actually say like a time on the clock, not like it's been this many hours since yeah. So yeah, that question is, are you allowed to use a calculator on your exam? No. That kind of question is really kind of hard to make exam easy because you have to give them a number that's going to come out nice so that you can then subtract it from whatever time you found the body. But let's like, if, for example, we had a question like that and we say we found the body at, let's say, 10 a.m. And after doing all the work, we ended up showing that, well, the amount of time, and when you do this problem, you end up getting a negative value for time because you're kind of setting the temperature equal to a number that you would have had before all this process started. So we're typically thinking of this as like time equal to 0. And then after we do all the work, we end up getting something like, oh, the body died at time equal to negative 8.25. Again, I'm thinking of time in hours here. Apologies if I didn't say that. So time in hours. Great. So we have to go back 8.25 hours. So what's 10 minus 8.25? Looks like it's 1.75, right? So 1 o'clock and 75 minutes? That's not right. It's 1 hour or 1 a.m. and then 75% of the next hour towards 2 a.m. So you have to change that 75, right, that decimal, right? That's 75 hundredths of an hour or 3/4 of an hour, which is 45 minutes. So this would be 1:45 a.m. 8 hours and 15 minutes, or 8¼ hours before 10 a.m. So yeah, so unfortunately the decimal there, you have to think about the decimal turning into minutes, which minutes are base 60 and decimals are base 100. So there's a conversion there that you have to think about. But again, in my opinion, this kind of question is hard to ask well on an exam. Not that Dedel couldn't do it, but it's not what I would expect to see. Sure. So do you mean like drawing a graph or like, maybe. um, sure. So I'm just trying to think of, let's see here. Sure. Let's see what I can come up with here. Use a different color. This is going to be an annoying question. Sorry, my graph got too big. Okay. And let me label some numbers here. Let's see. Let's make this a -1, a -2. And then 1, 2, 3, 4, 5. Just so you can see everything here. Hopefully everyone can see what's going on. All right. So the question is, where is this function? Let's call it f of x. Where is f of x continuous? Or really, where is it not continuous? So going from left to right, where is it not continuous? What's the leftmost place where it's not continuous? -2. And then where? And then where? What about the corner? What's the difference between a cusp and a corner anyway? Nah, it's a cusp is more like when the graph is still curvy but pointy, where a cusp is more, or a corner is where it's more like straight and just makes a sharp turn kind of. So there is a better definition, I'm sure, somewhere, but that's kind of my definition. Corner looks more like a hard right angle, whereas a cusp looks like you're both coming to like a very vertical point typically. So good question. In fact, you know what? We'll follow up with an even better question. We're also going to ask, where is this function differentiable? So I will point out this function is certainly continuous at, let's say that this is -3 over here. It would have been smarter to label that to kind of give you the illusion of, oh, maybe we should not include it. But right, so definitely continuous there because we didn't lift our pen off the paper when we were drawing it. But when we talk about differentiability, we will not include that point. So it's not continuous at -2, +1, +3, and +5. So writing where it is continuous is kind of super annoying. It's continuous on the interval from -infinity up to -2, and then -2 to +1, and then +1 to +3, and then +3 to +5, and then +5 to infinity. And none of those get included because even though the function is certainly defined everywhere, right, it's not continuous at 3 because the left-hand side and the right-hand side don't match up. So even though the function's defined at 3, it is not continuous at 3. Sure, and I certainly didn't include, so almost every discontinuity I drew here is a jump discontinuity. In fact, all of them are. So these are all jump discontinuities. We'll do another example in a second, or we'll look at another example with some different types because this is the type I think of first when I'm thinking about discontinuities. But let's ask the other question. Where is f of x differentiable? Well, certainly It's not differentiable at all the places it's not continuous, right? Continuity is a requirement for differentiability. So we're certainly not differentiable at the same places. So we're not differentiable also at -2, 1, 3, and 5, as well as -3 because of the corner at -3. So here we would say it's differentiable on the interval from -infinity to -3, union -3 to -2, union the same rest of this here, -2 to 1, union 1 to 3, union 3 to 5, union 5 to infinity. Probably a bit more discontinuity than we really needed to see, but kind of went crazy. So those are jump discontinuities. In my opinion, there's two other types of discontinuities. That's right, yeah. So we'll just draw a function that has both of them. So let's be a little more specific with what you're doing, James. So here we have the following. Yeah, I think that looks all right. So here's another function. Let's call it g of x, where we want to talk about both the discontinuities and the differentiability. So labeling these things here, that's 3, 2, 1, -1, -2, -3. So everywhere we have a vertical asymptote, the function is discontinuous, right? Whether it's defined there or not. So technically, you can draw something kind of weird where you actually have it defined. You could totally be like, yeah, I'm going to put a point right there and say, well, it's defined at -3. It's still not continuous there. Usually that doesn't happen though, right? Usually you don't have a thing defined on the vertical asymptote, but you can totally make up weird piecewise functions that do anything you want. So you could have a function like this where you had a point on the vertical asymptote, annoyingly so. So I would say that g of x, apologies, is not continuous at the following places. X equal to -3. Technically not because it's undefined, but because the limit doesn't exist. The limit as x, I should write the actual notation here. The limit as x approaches -3 of g of x does not exist. Now yes. Right, is infinity a real number? No, it's not. So for the limit to exist, it has to be equal to an actual finite real number. So you're correct, very correct, in that if someone asked you about this limit, you should all say it's equal to infinity. But you should also know that that means the limit doesn't exist. Which I know feels kind of like we're saying different things. We're not. We're saying the same thing. We're being more specific about the way the limit doesn't exist. We're saying, yeah, the limit doesn't exist, and also the function goes up to infinity. Right? But it's not actually getting close to one number, right? It just keeps going up and up and up and up and up and up. Normally, you would just say the function, the limit didn't exist because the function was undefined there. I should say, you would say that the function is not continuous there because the function is not defined there. Like we're going to say over at +1. So not continuous at x equals -3. I guess we'll go from left to right, though. It's not continuous at x equal to -1 because even though the function exists and the limit exists, they're not the same. So this is called a removable discontinuity because the limit as x approaches -1 of g of x, which would be 0, does not equal g of 0, which would be 2. Sorry, g of -1. Sorry about that. Right, for the function to be continuous, the limit value and the function value have to be the same. And if they're not, it's typically called a removable discontinuity. Over here at 1, we also have a vertical asymptote. I would say that It's not continuous at 1 because it's not defined. G of x is not defined for x equal to 1. And again, to be continuous, there are 3 conditions that have to be met. It has to be defined, limit has to exist, and they have to equal each other. So if any one of those 3 things doesn't match up or happen, then it's not continuous. Lastly, at 3, also not continuous, again, for the same reason. G of x is not defined at 3. Yeah, so that is also removable. So a removable discontinuity is a removable discontinuity if you can make it continuous by filling in 1 point. That's why a jump discontinuity is not a removable discontinuity, right? Because for a jump discontinuity like this, if you filled in a point, right, you still couldn't make it continuous. So here we'd say it's continuous on negative infinity to negative 3 union negative 3 to negative 1 union negative 1 to 1 union 1 to 3 union 3 to infinity. Like on the previous one, right? These are all examples of non-removable discontinuities because you can't just think about removing or adding back in a point to make it continuous. Whereas for this new one, there are 2 places where we could either put in a point or change where a point is to make it continuous. Right? If I move this point here, it'd be continuous at negative 1. If I put in a point right there, it'd be continuous at positive 3. I will also point out the interval of differentiability is the same. Right? This function is differentiable on the same interval from negative infinity up to negative 3, from negative 3 to negative 1, from negative 1 to positive 1, from 1 to 3, and from 3 onward. What's the domain of this function? Or a better question, what values do I need to include in the domain that were not included in the where it's continuous? Negative 1 is certainly one of them. Negative 3, I know it's hard to see, but I did say there's a point there. So technically the domain here would be everything from negative infinity up to 1, union 1 to 3, union 3 to infinity. Right, we're just talking about places where it's defined. Doesn't have to be continuous there, just to be defined there. Just to be a point on the graph for that x value. All right. Yeah.
I'm confused about your definition of a removable discontinuity.
Sure.
How would we move the point at x equals negative 3 to make it?
I didn't say negative 3. Okay. So negative 1 is removable, and positive 3 is removable.
So what type of discontinuity?
Weird. Negative 3 is something you don't see typically. Like I made up something strange here. Usually you don't have a point on a vertical asymptote. And not that you couldn't ever, it's just not typical. So usually there wouldn't be a point there, and we would just say it's discontinuous because it's undefined.
So we wouldn't call that a...
No, because there's nowhere I can put that point that makes it continuous, right? I can't put the point up at negative 3 infinity, right? I can't go that high. There's no point to actually draw it in, which is why the limit being infinity means the limit doesn't exist. Yeah, that's kind of a weird example that I would encourage you not to focus too much on. Sure. So what kind of function are we thinking? Like a regular function, or a more typical example would be a piecewise function? Both. Well, for regular functions, so for quote unquote regular functions, I know that's a very kind of loaded word there. But for regular functions, meaning typical looking things that are not piecewise, most functions are continuous on their domains. So for example, if I gave you f of x equal to, Sure. X squared plus 2x minus 3 over x cubed minus, yeah, I don't love that choice, minus 16x, and asked, where is this continuous? Well, f of x is a rational function, and rational functions are continuous where they're defined. So we have to figure out what the domain for this function is. So really, we're just worried about, well, where is the denominator equal to 0? Great, this is a factoring problem. Factor out an x. Factor that more. X squared minus 16 factors is x minus 4 times x plus 4. So what's not in our domain? 0, 4, and negative 4. So then the intervals, or I should say f of x, is continuous on, well, let's draw it here so I don't mess it up. 0 in the middle, negative 4 on the left, positive 4 on the right. Everything that doesn't include those 3 points. So everything from negative infinity to negative 4, union negative 4 to 0, union 0 to 4, union 4 to infinity. So typically, when asked about, again, I know this is very generic, regular looking functions where they're continuous, you typically look for what their domain is. And when you look for what their domain is, you adhere to the 3 things, right? You look for potential division by 0, potential square roots of negatives, potential logarithms of 0 or negatives. So just to give you one more example, if I said the same question, where is a g of x equal to the square root of x minus 3 over x, yeah, let's make this x squared minus 25, let's say 36. Where is this function continuous? Sorry. This function, this has an answer we might not like. That's all right, though. So let's think about where we might be dividing by 0. So what values of x can we definitely not have if we want to not divide by 0? Right, we definitely don't want 6 or negative 6. So x can't equal 6, can't equal negative 6. So I'm already thinking about drawing my number line here. I definitely don't want 6 or negative 6. They're out. But also, we have the square root of x minus 3. We have to say, oh, additionally, x minus 3 better be bigger than or equal to 0. So x better be bigger than or equal to 3. So over here at 3, we're including 3, and then we're actually cutting off everything over here. We don't want any of that. So it's not even a concern that negative 6 is not even in a realm of thinking, really. Like, it's out of bounds already. So then we want everything from 3 to 6, excluding 6, and then anything from 6 onwards. So we would say, and I would say this function is continuous on the interval from bracket 3 to 6, union 6 to infinity. The bracket is a little maybe concerning, but I will point out that we typically say, so just to kind of assuage your fears about this particular example, if I asked you for f of x equal to the square root of x, which looks like this, where this function is continuous, we would say that it's continuous on the interval from including 0 all the way to infinity. And there's this whole kind of weird thing about, like, if a function's only defined on one side of a point, we say it's continuous there as long as the things kind of make sense, like as long as the limit from the correct side approaches the value. The problem with this example here is, typically when we talk about a function being continuous somewhere, the function has to exist at 0. Cool, it does. The limit usually from both sides has to exist, but that's not something that can happen here because it's not defined on one side. So we kind of just don't worry about it. So again, I'll say, to answer your question very broadly, regular functions are continuous on their domains. But then, if anyone's asking you about continuity, they're almost for sure going to ask you some sort of piecewise thing. So usually, we ask a question like, where is the following f of x equal to? Oh yeah, let's do that. That's a good question. Where is f of x equal to, let's see, 2x plus 1. 1 is not my favorite there. Let's say 2x plus 4 when x is less than or equal to 0. It's equal to sine of 8x over 2x when x is bigger than 0 and less than, I don't love this choice, but fine, less than pi over 2, sure. And then, yeah, that'll be interesting. Cosine of x when x is bigger than or equal to pi over 2. So where is this function continuous? So before you get started here, you should look, it feels like it's really hard to see all of a sudden. Is it still fine to see? To me, it looks weird. Okay. Before you get started answering this question, you should ask yourself, are any of the functions on their own discontinuous somewhere? Well, no, 2x plus 4 is fine. Sine 8x over 2x would be discontinuous where? At what value of x? 0. Luckily, it's not defined when x is equal to 0, right? That's not part of the domain it's defined on. So as far as we're concerned, this function is defined everywhere that we have said its domain for. And cosine x is continuous everywhere, different, right? So most of the pieces in your piecewise function will either be defined everywhere or at least defined on the interval that they are defined on, which I know is stupid language, but whatever. So the only places we're almost ever concerned about continuity for a piecewise function are where you switch from one piece to the next piece. That's usually the deal. So we are concerned about what's happening at x equal to 0. So we're going to do 3 things. We're going to see what f of 0 is, we're going to see what the limit is, and we're going to see if they both exist, if they're equal to each other. So f of 0. We'll plug it into the piece that I need to plug it into, which is the first piece here. So f of 0 is going to be 2 times 0 plus 4, which is 4. The limit part. So usually the limit from the same side of the piece you already used isn't a question, right? Like if I look at the limit as x approaches 0 from the left, well, that's just where I'm using the piece where x is less than 0, which is the piece I already used to find the function value. So it should end up being the same, right? The limit as x approaches 0 from the left of 2x plus 4 is just going to be 2 times 0 plus 4. The other side is what's really in question. The limit as x approaches 0 from the right of f of x is the limit as x approaches 0 from the right of sine of 8x over 2x. Now, often the other side limit is also something you can easily plug in. This is not true in this case, right? We can't just plug in 0 here. You get 0 over 0. Oh, I'm getting 0 over 0. What could I use? L'Hopital's rule. You could also do this the old school way where you do sine of 8x over 8x times 8x over 2x if you wanted to do it the wish method like we used to do. But I would use L'Hopital's rule here. Using L'Hopital's rule, we get the limit as x approaches 0 from the right. The derivative of sine of 8x is cosine of 8x times 8. The derivative of 2x is 2. And now if we plug in 0, we get cosine of 0, which is 1 times 8 over 2. And 1 times 8 over 2 is also 4. Those are the same, so the limit exists. So the limit as x approaches 0 of f of x is 4. Now, it's not enough for the limit to just exist. We also have to at least say something about how, oh yeah, the function value being 4 and the limit value also being 4 means they're the same, so the function is continuous at 0. So we can say f of x is continuous at x equal to 0 because the limit as x approaches 0 of f of x is equal to f of 0. And if they're asking a question like this, where there's 2 places where it's switching, almost always, one of them will be continuous and one of them will not be continuous. It's just like the way these problems get written. I don't think I've ever written one of these for a test where they've both been continuous or they've both been discontinuous on purpose. Maybe occasionally I made a mistake on accident and they were both discontinuous. Oh well. But almost always, if one of them's continuous, you still have to show the work, but it's a pretty good bet that the other one's going to be discontinuous. So let's check. So now I'm looking at pi over 2. So f of pi over 2 is equal to cosine of pi over 2, which is 0. This might actually be, I might have made a mistake. These might actually have been both be continuous. Sometimes that happens. Let's find out. So second part, the limit. The limit as x approaches pi over 2 from the right. And I always like to do the first side I've already kind of decided that uses the piece I've already used because I just find it easier to do first. So from the right, that's using the cosine x piece because that's where x is right of pi over 2. That's still going to be cosine of pi over 2, which is 0. The limit as x approaches pi over 2 from the left, which is not the cosine piece, is equal to the limit as x approaches pi over 2 from the left of sine of 8x over 2x. Unlike before, where we couldn't just plug in 0, we can just plug in pi over 2. So we're going to get sine of 8 times pi over 2 over 2 times pi over 2. So that's going to be sine of 4 pi over pi. But sine of 4 pi is 0. Right? It's 2 full revolutions around the unit circle. Get you back to 0. So atypically here, right? Not on purpose, but certainly it can happen. This one is also continuous at x equal to pi over 2 because we see that, again, the limit as x approaches the value of interest is equal to the function at that value. So in this particular example, we would say, well, it's continuous everywhere. So f of x is continuous on the interval from negative infinity to infinity. Sometimes that can happen. All right. So I do think I need to spend more than a few minutes talking about antiderivatives, just so that everyone is understanding what's kind of expected as far as antiderivatives. So antiderivatives. Here's the thing, at least as far as we're concerned, this is not necessarily true in 17b because eventually you'll learn how to find the antiderivative of very complicated functions. But at this juncture, you already know a lot of antiderivatives because you know a lot of derivatives. So I'll point out, you know that the derivative of, say, I don't know, x to the 4th power is equal to 4x cubed. So in a similar way, and the notation here is kind of sucky until we get to the next quarter, unfortunately. So typically we would say that if f of x is equal to 4x cubed, then the antiderivative, which we will call capital F of x, is capital F of x equal to x to the 4th. Because it undoes the derivative, right? If you took the derivative of the antiderivative, you get back to the function you started with. But it's not the whole story. Because if I said it was x to the 4th plus 1, the derivative would still be 4x cubed. Or if it was x to the 4th plus 7, the derivative would still be 4x cubed. So typically when you're finding general antiderivatives, we add on a plus c to signify that you could add on any constant and it wouldn't change the value of the derivative. So there's a couple ways of writing this. I could either say, given f of x equal to, let's find something else fun, like x to the 7th plus cosine of x, find the antiderivative. Here's an equivalent way of phrasing it that looks a little bit different. I want to write this 2 ways just so you can see both ways of phrasing it. Given f prime of x equal to x to the 7th plus cosine of x, find f of x. These questions say the same thing. They're just saying, given a function, find its antiderivative. They're just phrased slightly differently. But right, f of x should definitely be the antiderivative of the derivative of f prime of x. And capital F of x is the notation for the antiderivative of a regular f of x, or lowercase f of x. In either case, the antiderivative here, well, it's going to be capital F of x equal to, for powers of x, the derivative decreases the power by 1. The antiderivative increases the power by 1 to counteract that. So our new power should be x to the 8th. But that's not quite right, because the derivative of x to the 8th is not just x to the 7th, it's 8 times x to the 7th. So we have to divide by 8 to undo the eventual multiplication by 8. So it's going to be x to the 8th divided by 8, or if you prefer, you can write it as 1/8 times x to the 8th. They're both good. Okay, so when I ask the question, what's the antiderivative of cosine? The words I actually say in my head is, what function can I take the derivative of to get cosine? What can I take the derivative of to get cosine? Positive sign. So that's the antiderivative of cosine. It's literally just this back and forth. It's kind of similar-ish to inverse functions. How inverse functions undo what the other one does. Derivatives and antiderivatives undo each other to get you back to the same function you started with. So the antiderivative of cosine is sine, because if we took the derivative of sine, we would get cosine. Down here, if I was writing it this way, I would write little f of x equals x to the 8th over 8 plus sine of x. We'll see. So there's a whole host of things you know how to find the antiderivative of. Like any derivative you know. So let's make a little bit of a list here. So let's actually start off with the anti-power rule, just so you all can see it. So the anti-power rule. So here's what we know. We know that the derivative of x to some power is that power times x to the power minus 1. And the antiderivative similar rule is that if f of x equals x to some power, then the antiderivative is equal to x to that power plus 1 divided by the new power. Let's see. Sorry. And that works for almost any power. But what power might be problematic? -1, right? If p was -1, then you end up dividing by 0. So this works as long as p is not equal to -1. So for example, we could be given, say, f prime of x equal to, sure, let's make something interesting, 2x cubed plus 5 over x to the 7th plus the square root of x minus x to the 2/3 power, and asked to find the antiderivative. Well, most of the things we say about antiderivatives are also true for derivatives, or vice versa. Most of the things we've said about derivatives are also true for antiderivatives, meaning it's often in your best interest to simplify your expression before you start trying to find its antiderivative. Here, I definitely should rewrite this as 2x cubed plus 5 times x to the -7th plus x to the 1/2 minus x to the 2/3. So that now I can more easily apply this idea. So now my antiderivative f of x is going to equal 2 times x to the 4th over 4 plus 5 times x to the -7 plus 1 is -6 divided by -6 plus x to the 1/2 plus 1 is 3/2 divided by 3/2 minus x to the 2/3 plus 1 is 2/3 plus 3/3, which is 5/3 divided by 5/3. Let's see. Now, almost always when we have these expressions where you're dividing by a fraction, it is it's pretty much expected that you're going to flip and multiply here, right? No one would ever leave it like this. You would always write it as 2/3 times x to the 3/2. So let's simplify this a little bit. F of x is going to equal 2 divided by 4 is 1/2. So you can either write this as 1/2 times x to the 4th or x to the 4th over 2 minus 5/6 times x to the -6 plus 2/3 times x to the 3/2 minus 3/5 times x to the 5/3 plus c. I will point out, just like with derivatives, we just use the constant multiple rule and the addition and subtraction rule, the sum difference rule, without even thinking about it, right? When you're adding things together, you just differentiate or anti-differentiate them as you would, and then add or subtract the results together. And constant multiples, just like they did for derivatives, just hang out in front like they do for antiderivatives as well. All right. A few more antiderivatives. Really, the list of every derivative you know is also the list of every antiderivative you know. So let's look at this list here. So here's our, how do I want to write this? Yeah, let's do it this way. So here's our function, and here's our derivative. So again, we have, let's see, where do I want to start? Let's start with e to the x. The derivative of e to the x is e to the x. The derivative of the natural log of x is 1 over x. The derivative of, let's do the trig functions. Sine of x is cosine of x. Cosine of x is negative sine of x. Tangent of x is secant squared of x. Cotangent of x is negative cosecant squared of x. Secant of x is secant x tangent x. And finally, cosecant of x is cosecant x cotangent x. Sorry, negative cosecant x cotangent x. One more for the road. Arctangent of x is 1 over 1 plus x squared. That's pretty much, I mean, again, there's a few other like different bases and whatever. So if these are all our derivatives, then great. So this is our list of derivatives. Our list of antiderivatives is virtually the same. Not exactly, which is why I'm writing it down. If it was exactly the same, I wouldn't spend time doing this. So for antiderivatives, we're basically just reading this table from right to left instead of from left to right. Right? Derivative takes you that way. Antiderivative takes you that way. In fact, that's an excellent thing to write. A derivative takes you from a function to the derivative. An antiderivative takes you from the derivative back to the function. So looking at this right side of the column, if the function is e to the x, the antiderivative is e to the x plus a constant. If your function is 1 over x, your antiderivative is the natural log of, okay, there's something I should say here. It's technically the natural log of the absolute value of x. I don't really want to get into why, because it's not a big deal right now, but technically there should be an absolute value of x there. It's really because we want the domains to match, but there's more to it, which we'll talk about next quarter. The antiderivative cosine of x is sine of x plus c. I don't want to talk about the antiderivative of negative sine. I want to talk about the antiderivative of positive sine. So since the antiderivative of negative 1 times sine is positive cosine, the antiderivative of positive sine is negative 1 times cosine. Which again makes sense because the derivative of negative cosine should be negative sine, which is positive sine. The antiderivative of secant squared x is tangent of x plus c. The antiderivative of positive cosecant squared x is negative cotangent of x plus c. The antiderivative of secant x tangent x is secant of x. The antiderivative of positive cosecant x cotangent x is negative cosecant of x. And the antiderivative of 1 over 1 plus x squared is the arctangent of x. Oh, sorry, plus c. So there is a, not exhaustive, but as far as we're concerned for now, a pretty exhaustive list of all the things we can anti-differentiate. Later on, next quarter, we will also learn how to find like the antiderivative of just tangent or just secant, right? Those are things we don't know yet because they're not things that come up as derivatives that we recognize, right? We don't have a function whose derivative is equal to secant yet. So to me, that kind of leaves us with, oh, there's something. asking a question like, so let's move this here, apologies. Find so if someone writes a capital, you should assume they mean antiderivative, unless they're saying something else. Find f of x for the original function being, I don't know, let's say secant squared of x plus x to the fifth minus 1 over 1 plus x squared. Sure. That shouldn't be too terrible. So let's see, f of x is going to equal the antiderivative of secant squared of x is tangent of x. The antiderivative of x to the fifth is x to the sixth over 6. And the antiderivative of 1 over 1 plus x squared is the arc tangent of x. Let's see. I don't know how much you're expected to know, but let me look at one more example here. Let's say our function that we want to anti-differentiate is, yeah, let's do that. Let's say it's cosine of 4x. And again, I don't know if eventually you'll have to do this, so it's not terrible to say it right now. I just don't know how into antiderivatives Vidal is going to get tomorrow. I assume he's talking about it tomorrow. Maybe, I don't know. Maybe not. Maybe he's not really much for doing a review in class, right? No. So what else is he going to talk about? Probably antiderivatives. So I want to find the antiderivative of this function. And actually, I will point out this idea that I'm about to mention here in the last 3 minutes of class is super useful for next quarter, if not for your final exam, but certainly for next quarter. So what's the antiderivative of cosine of 4x? Well, ignore the 4x for a minute. What's the antiderivative of just cosine of x? Good old sine of x. So the thing about the argument of a function is really you can't change it, right? That 4x doesn't get to change. It is stuck inside that function. It is what it is. But if we say that our antiderivative is just sine of 4x, that's not going to cut it. Because if I just leave it like that, what's the derivative using the chain rule of sine of 4x? Right, it's cosine of 4x times, which isn't that. That's a problem, right? If something is an antiderivative, its derivative should get you exactly back to the function that you wanted to be taking the antiderivative in the first place. So how do we adjust for having to multiply by 4 after we differentiate? Dividing by 4 or multiplying by 1/4. And that fixes it. So this idea comes up a lot, that if when you differentiate, you end up having to multiply by a constant, then your antiderivative, you need to be dividing by that constant. Almost always true. I will give you one more example here, just because I think it's worthwhile. So if your function was equal to e to the 6x, we know that the antiderivative of e to the x is e to the x. The antiderivative of e to the 6x is probably going to be e to the 6x, but we're going to have to divide by 6 because the derivative would make you multiply by 6. So your antiderivative here would be 1/6 e to the 6x. I prefer to write it as multiplying by 1/6. It is also perfectly fine to write it as e to the 6x divided by 6. I just think it's easier to think about taking the derivative of this because it's more obvious that you don't need to use the quotient rule here. Whereas this, you might accidentally tell yourself you need to use the quotient rule, which you really don't need to do. So I like writing it like that. All right, that's all I've got. I have office hours as usual today and tomorrow. So as far as next week goes, just so everybody knows, right, you don't have classes next week, just finals, no classes. We don't meet. Your other classes don't meet next week, just finals. I will have office hours. They'll be, I'll post them on Canvas. They'll all be in the library next week though. None of my regular office hours, they're all different next week. I'll post them on Canvas. And good luck on your final. Yeah, so both of these were like, so I'll point out the antiderivative f of x of little f of x we think of as capital F of x. And similarly, the antiderivative of f prime is regular f. They're just different ways of expressing the same thing. So if you're given little f, you should say the antiderivative is capital F. If you're given f prime, you should say the antiderivative is just f. In 17b, we'll have much nicer notation for the antiderivative. It's just we're not there yet. You're very welcome. Again, please do the evaluation. You're welcome.